So all right, let's start. Here we go. Okay, start. Ready to start. Okay. So this was one that was from Monday's assignment that had a low success rate. So let's talk about this. So they gave you this table of all these function values, and then they asked you, and then they told you that capital F of x was f of x. And they wanted you to find a derivative of capital F, a specific rate of change at x equals 2 for the function capital F. So what we need is we need this. So what if capital F is little f of x? Then what rule will apply to find the rate of change of capital F? Chain rule. Okay, so we said that it's the rate of change of the outside, exterior, with respect to the interior, then times the rate of change of the interior. So that's our chain rule that we use on a composite function. It doesn't matter if you're taking the function and plugging it into itself. It's still a composite function, and you still apply the chain rule the same way. So now if we want this at x equals 2, it's going to be the rate of change of f of, with respect to, or when x is f of 2, and then times the rate of change of f at 2. So now we need to just really know our function notation. We've tried to work hard on that this semester to really get function notation. We'll start with f of 2. What is f of 2? We come up here, when x is 2, f of 2 is 1. So that first term then will be the rate of change of f when the input is 1. What is that? So that's 4. So we're looking at now the rate of change of f when its input is 1. So this whole thing then is 4. And the rate of change of f when the input is 2. 5. So then this is equal to 20. This is really exercising your understanding of function notation. Function notation is used to represent output values, right? When you see f of something or f prime of something, that's an output value, right? Well, in the composition, then output becomes the input of another function. And that's what's happening here. Any questions on this one? Okay. Also on this was number 14. I don't know if we'll do this or not. Let's see. What's that? That was 12. This was Monday's homework. That was number 12. I'm guessing this one had lower success because you tried plugging in 4 into, once you found the rate of change of A, or the rate of change function, you plugged in R equals 4. But what? Yeah, 0.04. So you have to plug in the percent as a decimal. So if you find that rate of change function, if you plug 4 in, it won't be right. But if you plug 0.04 in, you'll get the right value of rate of change. So I'm guessing that's because hopefully this is by now, this is pretty straightforward. What would it be? It would be 800, let's just do it anyway. 800, so the rate of change would be 800 times 36 times 1 plus 1/12 to the 35th by the chain rule. And now for part A, you're going to plug in 0.04. You need the decimal version of the percent. Questions on that? Okay, and then there was one from today's that was, let's go back to that. due today, November 5th. Number 13. Okay, and so this hopefully is a very straightforward rate of change function to find, but the problem is, how do you express log base 5 in web work? That's probably where we're in trouble. So let's just do it. So first of all, overall structure. Product. It's one function times another. So we're going to apply the product rule, which says take the first times the rate of change of the second, which will be 1 over x and ln of 5. Plus the second times the rate of change of the first, which is rate of change of 6 to the x. 6 to the x, remember that we did this little investigation. We found that the rate of change of an exponential function is just a constant multiple of the original function. And ln of 6. Okay, so I think maybe the difficulty here was then, how do we put that into web work? How do we put that? Because if you put log, I think even Weber, you put log in, it means natural log. But there's a thing called the change of base formula, and the change of base formula says that that equals the log of any base that you want of x over the log of that same base of 5. So this would be, choose any base that you want, call it b, log base b of x divided by log base b of 5. So the easiest one would be to use natural log. So natural log of x over natural log of 5 is an alternative or equivalent way to express log base 5 of x. That's called the change of base rule. So that's probably why we ran into trouble. But the important thing for tonight is this first step. Are we good on the first step? Okay, so I want to do, let's have you do one more kind of ugly example of a chain rule problem. And then I want to tie lots of things together. The really important, maybe one of the most important discussions of the semester, which will tie a lot of things together. So, all right, take 5 minutes and see if you, by now, this is tonight. Could do something like this tonight. Take 5 minutes, see if you can do it. Go. That's right. Did I make a mistake? Yeah. Let's ask questions here. You can whisper. Whisper's okay. Just one second.
We can derive that from, right? 6 times 7 is to 10x. We derive it.
That is derivative. I am derivative.
So we need to use
This is now, I'm taking the derivative here, so I took 1 over this. So okay, so it's the rate of change of arc sine, 1 over square root of 1 minus the interior function squared, times the rate of change of the interior function, which is natural log. So it's going to be 1 over that times the rate of change of the interior function. So now I'm in this step, I'm at the rate of change of this, which is, whisper please, whisper, whisper. When I'm at the rate of change of this, I'm taking the rate of change, so this is a sum and difference. So rate of change of x to the 5th plus rate of change of this. Rate of change of exponential is, so first of all, constant multiple rule. Rate of change will be just, so for exponential, it's the constant times the function. But then by the chain rule, I also have the rate of change of the interior function, secant squared. So that is the rate of change of 6 times 7 tan x. That's the times. Does it answer it? So that thing, that's what that is. That's the rate of change of 6 times 7 to the tan x. Other questions? Yes, oh, sorry. So, whisper. So if you're, whisper. Don't let your vocal cords vibrate. All right. So this rate of change is with respect to x. So we think about how the output of j is changing as x changes. So as x changes, what does this thing do? Stay the same. It stays the same. It doesn't. X changing doesn't change ln of 10 b to the negative 1/4. So in essence, that thing is just a constant. So we're doing the rate of change with respect to x. With respect to x. So we're thinking about how the output of j changes, how fast the output changes when x changes.
Okay, so because this b is just like another constant.
It's some other thing that doesn't change when x changes.
Okay.
So that represents a constant. There was another question over here? That same question. So remember, constants. Pi to the 8th. E to the negative 2, ln of 7. Make sure you know that these things are numbers. Things like these are numbers. You're not going to apply some power rule or natural log rule. These are values. They're constant, so the rate of change is 0. Yes? No, because no. I was just showing where that came, that I didn't forget it. Okay. So saying -0 or not putting it is the same thing. Other questions? Okay, so we'll have I'm gonna do a context situation, and we'll have one more practice kind of problem as part of that. But in the broader conversation, I want to tie a lot of things together here, and so this material from this next part is not on the mastery test. I think we got the flavor of the mastery test now. But it will be on Monday's quiz. Okay, so what we do now is all fair game for Monday's quiz. All right, so here's the situation. When a ground fault opens, scientists begin measuring the width of the opening in centimeters at a certain point along the fault. They take regular measurements for several months and model the data with a function W, whose graph is shown below. So I have 3 questions for you. Take about 2 minutes to answer, talk to the people. So there's going to be a series of about 6 or 7 questions here. Answering these questions is really about, do you really understand calculus or not? Being able to do derivatives is just very mechanical, and you could argue that's not really mathematics at all. Okay? Mathematics is about understanding and being able to reason and form conclusions about things, all right, about how quantities relate. So these questions are really about what calculus is all about. So your ability to answer these questions is a gauge of how well you understand calculus. Go, take 2 minutes for the first 3. Okay. When you look at the curve, what exactly are you looking at? How is the curve generated? What are you looking at when you look at that curve?
The width of the fault at any time.
What's that?
The width of the fault at any time.
The width of the fault at any time. So the width of the fault, a specific width at a specific time, how is it represented? What are you looking at when you look at a curve? Any curve. Oh, asked a good question, I guess. Points. This is how you should, when you see a curve, this is what you should be thinking. It's a bunch of points that emerge, in this case, as time goes by. Those points came about as months went by. So when you see it, you shouldn't see just, oh, it's a bent wire up there, inviting me to answer some math problems, right? No, it's the emergence of points as x increases. As x increases, points emerge according to this relationship. Okay? What does the point 6, 7.294 represent? See if I can get it on there. Okay? What does the point 6, 7.294, the point that I've stopped the animation at, what does it represent? Tell the person next to you. This is not a trivial question. It's not a trivial question. It's really important. Okay. What does it? Someone. How about in the back corner back there? What does the point 6, 7.294 represent? Tyson.
It's like after 6 months, the width grows about 7 centimeters.
Okay. He said after 6 months, since the fault opened, this was the width at that point in time. This is the width at that in centimeters at that point in time, right? And so the curve is a whole lot of those points, right, that represent a time and a corresponding width. Okay? Again, when you look at a curve, you know, you're given a picture like this. Imagine it like this. Imagine it like this. This is what calculus is about. Analyzing it happening dynamically. Happening dynamically. As x increases, how does the fault width in centimeters change? Okay, accumulation or rate of change function? Hopefully we know that's an accumulation function. The accumulation of width at this particular point at the fault. Okay, I got 2 more questions for you. Go. Okay, so this number 4, incredibly important question. Could you articulate what a rate of change function is, just in general? What is a rate of change function? Any volunteers want to give it a shot? What is a rate of change function? Jose?
The rate at which the accumulation is changing at any given x value.
So the rate at which the accumulation is changing at any given x value. Anybody else? That's pretty dang good. But anyone have a different way of saying it? Oh yeah, go ahead.
How fast two quantities are changing with respect to each other?
Okay, how 2 quantities are changing with respect to each other, but what about as a function? So when we're talking about a function, so that sounds just like rate of change. You're talking about rate of change, but what about a function?
How much y changes with respect to the change in x?
Okay, how much y changes with respect to the change in x? Again, you're just defining rate of change. So I'm asking, what is a rate of change function? What does that mean if it's a rate of change function? Is that a scratch or a... Yeah. Okay. What is a function? It has input and output. So we have an accumulation function. What's the input? Time in months elapsed. And for any given time in months, that function tells us the corresponding width of the fault. So if it's a rate of change function, it must have the same kind of thing. It must have a input. In this case, the input would be time in months. It's the same input, right? And what will the output of the rate of change function be? It'd be the rate of change at that moment. So rate of change at a moment. Okay, so it'd be given. So it's a It's a relationship of the input being time in months. And this goes to our column. So what would our columns be in our table? So we're going to make a table that represents a rate of change function. What will the first column, what quantity will the first column represent? X isn't a quantity. What quantity? Time since the fault originated. Okay? And what will the second column be? So given a time since the fault originated, we're going to have, for every time that we pick, those should be our corresponding fault width. For the rate of change function? Oh.
The change.
The change in width? Okay, so we know it's going to be, what should I write? It's going to be the rate of change of width. So our accumulation function, input is time since the fault originated, output is going to be the width, the quantity, the amount, right? And then if we develop a rate of change function, the input will be time since the fault originated, and now it'll be how fast that fault width is changing, the rate of change of fault width at that moment with respect to time. Okay? So now all we've got is the graph, and we want to make a rough table here that represents that function. Given a time, it spits out a rate of change. Given an x value, it spits out the rate of change. How are we going to do that? It's just having the graph.
The change in width divided by the change in time in months.
The change in width divided by the change in time in months.
According to the x.
According to the x.
Another x value.
And another x value.
Progressively.
Progressively. So for instance, we're going to come here and I'm going to say it's at 0.25. At a quarter of a month gone by. How can I get, all I have is this graph. How can I get a rough estimate for the rate of change of the width?
W 0.25 would give you a exact y value from the accumulation, and then you can find another x value to W of that next x value, and then find the delta y for the delta y.
Okay?
I was just going to use the graph to approximate what the output, the fault is at that point in time.
Okay.
And then divide that, and that's going to be your rate at that time.
So you're going to find a y value and take y divided by 0.25.
Yeah.
Is that right?
I would take the slope over extremely small changes of x for many points.
The slope over an extremely small change in x. What were we going to say?
Take the change in y for that change in x.
Okay.
And divide that to find the rate of change.
Okay. So many of you are getting it. So let's pause the video at the end here. Show the whole graph. So we want the rate of change at 0.25. So I'm going to come up here to 0.25, right about there. No, it's going to stand. We want the rate of change there. So it looks like about 2 centimeters of width. Does that 2 centimeters have anything to do with the rate of change there? No. So the rate of change is how fast the width is opening or closing. What is it doing here? Is it opening or closing? What's that? No, at 0.25 months, is the width opening or is it closing? Definitely opening. That it's going up, right? That width is increasing. So the width is opening at 2 months. That's what the graph tells us. So what are we going to do to get that rate of change? It's a little blurry, but you can see the grid lines. This is 0.25 months this way, and this is this vertically it's half a centimeter. Okay, so 0.25 months is this way, and that way is half a centimeter. So I want you to estimate the rate of change at 0.25 months. I'll move the cursor. which is right here. It's actually right here. That point right there. Can you estimate the rate of change so we get 1 point of our rate of change function? 1 point of our function. Can you do it? Go. This is a quarter month. Each horizontal is a quarter month, and each vertical is a half a centimeter. Quarter month, half a centimeter. And we're looking right there. Can you find the rate of change? Okay, so here's one. This is the way that I see that we could do it. Change in x could be from starting at that right there to about there is about half of a quarter. It's about half a box. About half a box from there to there. And when that change in x is half of a quarter, what's the change in y? 1/2 centimeter. So how would we find this rate of change? Half a centimeter divided by, was that 1/8 of a month? 1/8 of a month? So what do you get? Half divided by 8, is that 4? 4 centimeters per month? Someone else get it? You can estimate somewhere around 4 centimeters per month. Okay, write that down. Write that down. Oh, no, I can write it down too. Did you catch what we just did? Very close to that point, what happens is curves, when you zoom in, they become straight. So we can apply the idea of constant rate of change for a very small change in x to get the rate of change right there at that point. So I noticed that for 1/8 of a month, default increased about 2 centimeters. And so that would be 2 divided by, sorry, 0.5? What was it? Half. .5 centimeters in 0.125 months. And that's where I came up with it's a change in y over change in x, which some people were saying. Okay, so let's go fast here. So what about at 1? That's at 1 month. Go. What is estimate the rate of change right there? This is at 1 month. X equals 1 month. Estimate the rate of change. This one's easy. What is it? It's not 1. Remember, this way is a quarter of a month. This way is half a centimeter. So quarter of a month this way per grid line. Grid lines this way are half a centimeter. So this is pretty easy. You can use a change in x of a quarter, and you get a change in y of a half, about, right? It's pretty much. And what is that rate of change? Delta y over delta x. Is it 2? So here we are at 1, and our estimate is 2 centimeters per month. Okay, let's do 3. This is at. So what are we doing? We're building a function because a function is a collection of inputs and corresponding outputs. A function is and if it's a rate of change function, then those outputs are the rate of change at a moment of a particular accumulation. Okay, right there above the arrow. That's at x equals 3 months. Pass, go. This is x equals 3 months. Go. Okay, to make it easy on ourselves, let's do 1.5 this way, which would be how many months? 1.5 this way. Be 3/8 of a month. Be a quarter and a half. So we can go from here to here is 3/8 of a month, or 1.5 times a quarter, and then we'll just go ahead and take 0.5 centimeter, right? So as we're estimating, so that's fine. So we'll take 3/8 of a month, and the change in y would be 0.5 centimeter. 0.5 centimeter? This is an important change here. Negative. Negative half. What's happening to the fault now? It's getting smaller. So that rate of change will be negative. So anyone got the calculation? It's going to be at 3. So what did we say? 0.375 is the change in x. And 0.5 centimeter. But negative, right? What is that? Negative what? Nice and loud. Thank you. Okay, negative 1.3. So, and quick, we'll do one more. Oh no, so bad. Run this one. Come on. So how about at 6? Okay. Right there at 6. Yeah, I don't know.
To the right.
The right? This one? What's the right? This is 6? My other right. Okay, what is it? It's about, the blocks are about 1-to-1 of the blocks. So we're saying a change in x of a quarter month, 0.5 centimeter. Did we have that before? Quarter month, 0.5 centimeter. What is that, 2? So back at 6. Okay, so point by point, we're coming up with this is a function, right? Input and output. Change the input, you get a different output. Our outputs are rate of change. That's what a rate of change function is. So if we were to sketch this, sorry. Let's sketch the rate of change function. What would that mean? What's happening at the beginning to the rate of change? So the accumulation is increasing. Where am I? There I am. But what the accumulation is increasing, but what's happening to the rate of change? Decreasing. So we'll do rate in red, right? So I'm going to do it on the same axes. At 0.25, what's the rate of change? About 4. At 1, rate of change is? What about in between those two? What's happening to the rate of change? Dropping, right? And what about before that? The rate of change is even greater, right? So what are we doing? We're developing a rate of change function, just point by point. What about at 3? What's the rate of change? Negative 1.3. Something like this down here. Somewhere here, the rate of change is not changing, right? So it's right around 2, it's 0. And then there, and then back at 6, we're back at the rate of change is. Okay, so we're sketching the rate of change function. This is telling us how that accumulation is changing at any given time. Okay, and so then there was lots more cool stuff to do. So we'll just answer this. Here's actually what the accumulation function is. So we'll just pick it up Friday here, but if you want to practice and do that, derivative, using the rules, I'll stick around and see if you got it right. But bring your laptop with graphing calculator on Friday for the new stuff. Bring your laptop to class. I'll remind you in the email. You're coming to the testing center tonight between 6:15 and 7:30. Between 6:15 and 7:30.